अस्सलाम वालेकुम स्टूडेंट्स, वेलकम टू द स्कॉलर देन चैनल। आज हम सेकंड क्लास स्टार्ट कर रहे हैं रिगार्डिंग द कॉम्प्लेक्स नंबर्स। पिछली क्लास में हमने यूलर्स आइडेंटिटी को डिस्कस किया था और उसके डेरिवेशन को डिस्कस किया था। वहीं से हम ऑनवर्ड्स कंटिन्यू करते हैं और आज की क्लास में जो हमारे ऑब्जेक्टिव्स हैं दे आर इंट्रोडक्शन टू द कॉम्प्लेक्स नंबर्स, उसके बाद हम देखेंगे हाउ कैन वी प्लॉट अ कॉम्प्लेक्स नंबर, और उसके बाद हम देखेंगे हाउ कैन वी परफॉर्म सम अरिथमेटिक ऑपरेशंस ऑन कॉम्प्लेक्स नंबर्स। वन बाय वन हम इन टॉपिक्स में से गो थ्रू करते जाएंगे। हम स्टार्ट करते हैं कॉम्प्लेक्स नंबर्स के इंट्रोडक्शन से। लास्ट में पिछली क्लास में हमने यूलर्स आइडेंटिटी को डिस्कस किया था। मैं यहां पे यूलर्स आइडेंटिटी को दोबारा से लिख देता हूं। यूलर्स आइडेंटिटी या यूलर्स इक्वेशन दैट वाज दिस थिंग। अब अगर हम इस पिक्चर को देखें, ये जो पीछे मेरे पास एक्स वाई प्लेन है जिसको हम कार्टेशियन प्लेन भी बोलते हैं, हम जानते हैं कि हम इस कार्टेशियन प्लेन में किसी भी पॉइंट को आइडेंटिफाई कर सकते हैं यूजिंग इट्स हॉरिजॉन्टल एक्सिस, जिसको हम एक्स एक्सिस का नाम देंगे, और एक वर्टिकल एक्सिस दैट इज परपेंडिकुलर टू दिस हॉरिजॉन्टल एक्सिस जिसको हमने वाई एक्सिस का नाम दे दिया। हम इसको कार्टेशियन प्लेन क्यों कहते हैं? एक्चुअली दिस मेथड वाज डिवाइज्ड बाय द रेने डिस्कार्टिस अराउंड 16th century. He was a scientist or he is considered the father of the analytical geometry. In fact, he was the first person who merged the geometry and algebra together and created a new branch of mathematics, what we call the analytical geometry. He devised a method to locate a point in a plane using two coordinates called the horizontal coordinate names as x and the vertical coordinate names as y. So all these coordinates are equally spaced. So this is the intersection of these two axes which is called the origin. And the origin is having 0 point for x and 0 point for y. So it means this is our reference point from where we can start measuring the x-axis and the y-axis. So positive x-axis is moving towards the right hand side and the positive y-axis is moving towards the upward side. Similarly, negative x-axis is moving towards left hand side and the negative y-axis is moving towards the downward side. So if we follow this procedure, then we can see that we can divide our plane in 4 partitions, what we call the quadrants. Why so? Because each of this portion, the union of x and y at here, the union of x and y at here, here and here, is dividing or is producing the 1/4 of the entire plane. That's why we call each of this section as a quadrant. So this is called the quadrant number 1. If we move counterclockwise direction, then this would be the quadrant number 2, this is the quadrant number 3, and this one will be the quadrant number 4. So we can observe in quadrant number 1, both x and y are having positive values. In quadrant 2, x is negative, y is positive. In quadrant 3, both x and y are negative, and in quadrant number 4, x is positive, y is negative. So if I say mark a point at this very location in this plane, then we can see that this point is located at x equal 8, and along the vertical axis this point is located at y equal 6. So the coordinates of this point are 8, 6, where left hand coordinate is always representing the horizontal coordinate, the x coordinate, and the right hand side is always representing the vertical coordinate or the y coordinate. So 8 comma x is the address or the marking or identification of this point in this Cartesian plane. Similarly, we can point each location by appropriately assigning the x and y location to it. For example, we have used this point with coordinates 8 and 6, where 8 is the x coordinate, the distance of this point from the y axis towards the positive x axis, and this is the y coordinate, the distance of this point from the x axis towards the positive y axis. जिस तरीके से हमने यहाँ पे 8 और 6 दो रियल नंबर्स को यूज़ करके इस पॉइंट को आइडेंटिफाई किया है और उसमें हम x को 8 और y को 6 की वैल्यू दिए हैं, अगर इस पॉइंट का मैं इस ओरिजिन से डिस्टेंस मेजर करूँगा तो हम यहाँ से एक स्ट्रेट लाइन ड्रॉ कर सकते हैं। इस स्ट्रेट लाइन की विड्थ कितनी, आई मीन व्हाट वुड बी द लेंथ ऑफ दिस स्ट्रेट लाइन। चूंकि ओरिजिन के कोऑर्डिनेट्स हमने x इक्वल 0 y इक्वल 0 मार्क कर रखे हैं, तो हम एनालिटिकल ज्योमेट्री को यूज़ करके अगर देखेंगे तो हमारे पास इस लाइन की लेंथ, लेट कॉल दिस a, इस a की वैल्यू हो जाएगी 8 माइनस 0 होल स्क्वायर प्लस 6 माइनस 0 स्क्वायर अंडर रूट, एंड दिस इज इक्विवेलेंट टू राइट 8 square plus 6 square under root. So this will be a real number. This gives me, so this is a real number, so this gives me the actual length of this wire. Now if we apply some trigonometry over there, let me erase it and write it a new location, because students are complaining that due to the reflection they cannot appropriately see it. Let me write it at this point, that this length of A is x minus origin coordinates plus y minus origin coordinates under root. This is equal to 8 square plus 6 square under root. So this A will be a real number. Now there is a question. This under root would give me both positive and negative values. But because this is the length, so we will be measuring the length as a real positive number, so we would be discarding the negative value that would be obtained through this square root operation. Now using trigonometry, if we say that this line is making certain angle theta with the x-axis, then we can determine the length of this portion and the length of this portion. The length of this portion, what we call the horizontal coordinate of this line A, and the length of this portion, what we call the vertical coordinate or the vertical projection of this part A. The projection means if we shine the light from upward on this red line, then we will be observing a line or a shadow that would be cast by this red line on this x-axis equal to the length of this black line. And if we shine the light on this red line from the left hand side, then the shadow cast by this red light on this vertical axis on the right hand side will be equal to this red dotted line. So what would be the lengths of this red dotted line and this black line? This red dotted line's length will be A sine theta and its length will be A cosine theta. So these are the fundamentals that we can derive, or we can understand the why A sine theta and A cosine theta is here from the fundamental principles of right angle triangles trigonometry operation. So if we compare this thing, the A cosine theta term and A sine theta term with this thing, and if say I multiply this expression with certain constant A, say A is the length of this red line, then Euler's identity will take shape of this equation. From this we can say that this A cosine theta is equivalent to the x length, x coordinate of this line A, which is equal to 8. And this A sine theta is representing the y coordinate of this line, which is equal to 6 in this example. And if we want to determine this angle theta, then this angle theta can be determined as arctan of y over x or arctan of sin theta over cosine theta. This gives us over cosine theta. So this angle or this theta, this is called the argument of this line. A is the length of this line and this theta is called the argument of this line. Now imagine if we are aware, if we are given the values of A and this theta, then we can determine a point precisely in this coordinate system. Because if we are given the value of A and we are given the value of this theta, using theta and A, we can determine the x and y locations of this. X is equal to A cosine theta, because A and theta both are given to us, so we can determine the coordinate value x, and A and theta both are given, so we can determine the coordinate value of y. Once we are aware with the x and y, we can precisely determine a point in this xy plane. That is the beauty of this Cartesian plane, that we can represent a point not only using the real numbers but using also the trigonometric expressions as well. So we can see that there is a similarity between this Cartesian plane and the Euler's identity terms. That's why this A cosine theta and A sine theta, that is multiplied with I, this can be used to represent a specific type of number on this Cartesian plane. This specific type of number that can be represented in this way, this number is called complex number. So what is a complex number? A complex number is actually consisting on two real numbers that are interconnected or integrated with each other according to this representation, where x itself is a real number. And y is also a real number. So x and y can take any value. It can be positive, negative, it can be fractional, it can be integer. As a whole, joining this x and the product of iota and y, this entire composition is called a complex number. So this x is called the real part, and this y is called the imaginary part. Why so? Because this is behaving as a usual number we are familiar with in our everyday life. That's why we call it the real part or a real number. But y, once it is being multiplied with the iota, it doesn't give us a physical sense of this number according to the previous understanding or according to the historical understanding. That's why we call the y as imaginary part. Though both x and y are the real number in their actual place, but once we write these numbers according to this fashion, it creates a new form of number, what we call the complex number. So we can represent the complex numbers using this Cartesian coordinate system by renaming the coordinates such that x is renamed as real part or real axis, and the y would be renamed as imaginary part or imaginary axis. So there is nothing new in complex plane, the plane that would be containing a vertical axis in form of imaginary axis and a horizontal axis in form of the real axis. That plane is called a complex plane, and that complex plane is exactly similar to the Cartesian plane, with only one difference, that we are marking the x-axis and y-axis as imaginary axis on y-axis and real axis on x-axis. So Here are some examples of the complex numbers. Now consider we mark the vertical axis as imaginary axis and x-axis as real axis. So if we are given to plot a number, say 5 plus 7 iota in this complex plane, then we can mark this complex number as a point in this complex plane as 5 points along the x-axis and 7 points along the y-axis. So this will be the number that would be represented by this complex number, or this will be the point that would be represented by this complex number, because here this is x equal 5 and at this point this is x equal 7. So if we draw a line from origin to this point, then this angle called theta will be the argument of this complex number. And how can we determine this theta? This theta can be determined from this information as this thing. And what will be the length of this red line? That is called the magnitude of this complex number. The magnitude of this complex number is x coordinate square plus y coordinate square whole under root. So this relationship can be traced back to the Pythagorean theorem, where this length is 5 and this length is 7. So this 7 and 5 are making the sides of a right angle triangle, and if we have to determine the length of this hypotenuse, which is actually the magnitude of this complex number, that can be determined using 5 square plus 7 square whole under root equal to the length of this straight line. So there is another way to represent the complex number. Consider if I add an angle psi in the argument of this complex number, then this identity will take this shape. So this is another way to represent a complex number that contains another parameter. This parameter is called phase of this complex number. The phase of a complex number means कि वो complex number अपनी mean position से clockwise या counter clockwise कितना rotate हुआ है. अभी हम यहाँ पे psi के different values put करके इस behavior को diagrammatically observe करते हैं. Suppose we have this relation. And using trigonometric identities, we will be concluding to this point. So from this we can say this thing. So How we can diagrammatically represent this thing? From this we can see that the magnitude of this complex number, we know that this is representing a complex number with real part equal to this and imaginary part equal to this. This representation of complex number is called complex exponential representation. Yeah, in short, exponential representation. And this format or this representation method is called rectangular representation method. Yeah, rectangular form. Why we call it the rectangular form? Because we can easily separate out the real part or imaginary part, as we can easily separate the horizontal and vertical components on a Cartesian plane. So, if we draw this number, then the terms in parentheses are giving us the magnitude of 1 with phase equal theta. So, let me draw an arbitrary line to this point, for example, with length equal to 1. Why so? Because 1 is the magnitude of this complex number that is represented by the terms in the parentheses. The terms in parentheses are showing that the magnitude of this complex number is 1. So, how would you draw this entire complex number that is containing the negative sign? We can see that this number is representing this thing. So, once we multiply we take the negative of this length, if this length is, say, pointing from origin to this particular complex number p, then negative of this length will be opposite to this line with same length as 1, but the difference between this and its new position will be of pi radians. So, this number p prime and this number is p, these two numbers are situated at the 180 degrees difference from each other. So, length of these two numbers is equal. Why so? Because if we are multiplying this entire number with negative sign, the magnitude is not being changed, only the sign or the direction of this arrow is changed. One, if it is pointing towards the p in the first coordinate, then multiplying it with the negative 1, its direction will transform by 180 degrees counterclockwise, and this will shift from first quadrant to the third quadrant in that case, where both x and y, they will be negative. So, it means if we introduce a phase of pi radians in certain complex number, then its direction is reversed by 180 degrees in counterclockwise direction. Though it is true that if we draw this point P by rotating this line clockwise, then we shall also be arriving at this very point, but this would be equivalent to introduce the negative phi phase over there. If we introduce a negative pi phase over here, then we will be rotating this point P clockwise from this current position, and it will move to this position. Though if we use the positive pi or the negative pi, the image of this p prime point will be same in both cases, but once we are using the positive pi, the rotation of this p point will be according to the counterclockwise direction, and if we will be using the negative pi, then rotation of this point p will be according to the clockwise direction. So, from this we can clearly see that, say, if I replace this phase with 90 degrees or pi by 2 radians, then this p will move to the second quadrant, and the difference of phase between this p and its new value will be 90 degrees. That can be drawn here, something like this. So, this will be the p double prime, for example, and the angle between p and previous position and p double prime will be pi by 2 radians. So, this will be the direction of rotation of this angle in that case. So, I hope so This will give you an intuition how the complex numbers can be drawn on a complex plane and how their graphical behaviors are related with their mathematical representation. Now we move onward. जैसा कि अभी हमने पहले डिस्कस किया कि हम मैग्नीट्यूड और आर्गुमेंट की बेस पे कॉम्प्लेक्स प्लेन में किसी भी जगह किसी भी कॉम्प्लेक्स नंबर को प्रिसाइजली पॉइंट कर सकते हैं। इस वजह से हमारे पास ये एक और मैकेनिज्म है, एक और वे है कॉम्प्लेक्स नंबर को रिप्रेजेंट करने का। इस मेथड को जिसमें हम मैग्नीट्यूड कॉमा आर्गुमेंट के फॉर्मेट में नंबर लिखेंगे, दिस मेथड इज कॉल्ड और दिस रिप्रेजेंटेशन इज कॉल्ड पोलर फॉर्म और पोलर रिप्रेजेंटेशन। तो हमारे पास तीन कॉम्प्लेक्स नंबर्स की सेपरेट रिप्रेजेंटेशन हो गई। वन इज द पोलर फॉर्म दैट contains the magnitude and argument, then rectangular, that contains real part plus imaginary part, और तीसरा कॉम्प्लेक्स एक्सपोनेंशियल या इन शॉर्ट एक्सपोनेंशियल फॉर्म। इसमें e raised to power iota theta and this is the magnitude. So you can see that once we are given the magnitude and argument, we can precisely locate a point in the complex plane. If we are given x and y, we can precisely locate the point in xy plane, in a complex plane. And if we are given the exponential form like this, where we can determine what is the a and what is the theta, we can again precisely determine the point in complex plane. From here, we have to do a little bit working, or from there, we have to do a little bit working to actually determine the x and y. याद रखें कि जब भी हम इमेजिनरी इस कॉम्प्लेक्स प्लेन में किसी कॉम्प्लेक्स नंबर को पॉइंट करेंगे, तो असल में जो हमें चीज़ चाहिए ईजीएस्ट प्लॉटिंग के लिए, दैट इज इट्स रेक्टेंगुलर फॉर्म। हम यहाँ से भी डायरेक्टली ड्रॉ कर सकते हैं, यहाँ से भी डायरेक्टली ड्रॉ कर सकते हैं, लेकिन दिस सीम्स अ कन्वीनियंट वे टू ड्रॉ, इसलिए कि इसके अंदर एंगल इन्वॉल्व नहीं है। यहाँ पे और यहाँ पे हमारे पास एंगल या आर्गुमेंट इन्वॉल्व है, और एंगल को प्रिसाइजली किसी पेज पे ड्रॉ करना विदाउट प्रोट्रैक्टर इज अ चैलेंजिंग एक्टिविटी। जबकि हम x और y को एक स्ट्रेट लाइन एज के साथ या एक स्ट्रेट एज के साथ या रूलर के साथ इजीली पॉइंट आउट कर सकते हैं, इजीली ड्रॉ कर सकते हैं। तो वर्किंग विद और ड्रॉइंग द कॉम्प्लेक्स नंबर्स ऑन अ पेपर यूजिंग पेन एंड पेंसिल और ज्योमेट्रिकल इक्विपमेंट, this form is user friendly. So now we see how we can interchange these parameters. From this we can determine the a, that is equal to x square plus y square whole under root, and the argument theta can be calculated as tan inverse y over, and from here if we are given the value of a and theta, then we can determine the value of x as a cosine theta and value of y as a sine theta. So given the value of a and theta, we can determine x and y. Given the value of x and y, we can determine a and theta. Once we are given a and theta, using the same relationship, we can determine x and y from the polar form to the rectangular form as well. Now we move to the last topic of this class, that is the performing the arithmetic operations on the complex numbers. अगर मैं ये स्क्रीन यहाँ पे रखूँ तो आई होप सो आपको कोई प्रॉब्लम नहीं होगा, because the readability would be clear if I keep on writing on this image. Well, first we start with the addition and subtraction operation, the most fundamental arithmetic operation. Consider we are given a complex number in rectangular form and another complex number in rectangular form. The real part of this complex number is A, imaginary part is B. Real part of this complex number is X and the imaginary part is Y. So, if we perform this operation, then this gives us like this. So, the real part will be added in the real part, imaginary part will be added in the imaginary part. So, this is straightforward. This is exactly identical to our normal algebraic expression. Say, if I write as one number and ask you to write and solve this, definitely that the coefficients of this variable A will be added together, the coefficients of this B will be added together, and this will be the result from this expression. Similarly, we are adding the real part in real part, imaginary part in imaginary part, and the result will also be a complex number. So, similarly we can perform the subtraction over here. Now let's take a graphical example of this approach. Consider I am having I have to perform this addition on two complex number. One is or say -2 minus 5i. First let's draw these numbers on complex plane. So if we plot this number, then we can point out this number precisely at this location. So this is x equal 3 and y equal 4. So we draw a line from origin to that marks the magnitude of this complex number. And we place an arrow at the location where this complex number is placed, such that these lines become a vector with direction deterministic using this argument theta, and its magnitude will be the 3 square plus 4 square whole under root. So this red line is now representing a vector with a magnitude and with a direction. Direction is represented by the argument of this complex number. We just saw how we can calculate the argument of a complex number if we are given a complex number in Cartesian format or rectangular format. And the length of this vector is representing the magnitude, that we know that how we can determine the magnitude of a complex number if a number is given in rectangular form. Now let's draw another complex number, that is -2, -5. So this number will definitely be drawn in third quadrant because both real and imaginary parts are negative. So this will be the location of this number. This is -5 on imaginary axis and -2 on real axis. And we draw another vector from this point to here. Now, what do you expect from the summation of these two complex numbers? The summation of these two complex numbers is exactly identical to the vector addition rule, that we can add this red vector and this black vector using head and tail rule. So if we apply the head and tail rule on these two vectors, like this. If we draw a vector parallel to this thing and a length, let me draw a precise vector, same magnitude and same length, then perhaps this will be adding at this point, and this length will be the summation or result. This point at this location, which is being pointed from the origin to this particular point, let me call this point P. The coordinates of this point P should be the result of this summation. And if we perform the summation according to the principle we just observed, this gives us 1 n minus I. So 3 minus 2 is 1 and 4 minus 5 is minus I or minus iota. This gives that x is positive, y is negative. So which means that if we could accurately draw this vector, then this red line should slightly move downward to make the x positive and y negative. Because we have not precisely drawn this blue vector, which is actually the replacement of which is actually drawn by displacing this red vector to this position. Actually, this blue vector should be ending slightly at this point here. So if we end this vector at this point, then this line should be drawn according to the scale like this. So you can see that the point P that is actually produced by adding these two vectors is lying roughly at this location. That if we are working precisely on a graph paper, then we would be arriving exactly at this conclusion. So that's how the addition of vector is being represented in graphical format, that is exactly identical to the vector addition. Now we move to the multiplication. Say I have a complex number a plus b iota that is to be multiplied with another complex number x plus y iota. So the multiplication is straightforward as the addition and subtraction work. Ax ay iota xb iota plus by iota square. This iota square we have seen, because iota is the under root minus 1, so iota square should be minus 1. So this leads to or this will be the real part of the resultant complex number and this will be the imaginary part of the product or resultant complex number. So it seems that if we multiply two vectors or two complex numbers in their rectangular form, the operation is quite lengthy and it's of course time taking. Once it is time taking, the chance of error is also bigger. So the multiplication gives us an easier way if we transform this rectangular coordinates into the exponential coordinates or in an exponential form. Here we can see that, say this number is represented as a e raised to power iota theta, where theta is the argument of this number and the a is the magnitude of this number. It is multiplied with e raised to power I phi, where b is the magnitude of this complex number and phi is the argument of this complex number. From this it seems very straightforward that the result would be a into b theta plus phi. And from this we can straightforward determine their rectangular coordinates as AB cosine of theta plus phi plus AB sine of theta plus phi. So this gives us the same result that we should be obtaining from this expression. So if say we have an example, say to multiply these two numbers, then we can verify these two identities or these two relationships by first evaluating the product of these two complex numbers following this way, and then by evaluating via this way and comparing the results. Similarly, from this we can perform division operation as well. Say we have two complex numbers like this. A plus bi is to be divided by x plus y iota. So working in rectangular coordinates, we can proceed this way. Before moving onwards, let's discuss an intermediate thing. That's a very important concept. Consider we have a number x plus yi. Its exponential form will be e raised to power I theta. The theta is tan inverse y over x. Now imagine if I just change the imaginary part, sign of the imaginary part, keeping real part as it is. Now recall the Euler's identity we discussed in our last class, that its complex exponential form will take this shape. Agreed? This number will be written in complex exponential form according to this. How? Refer to the previous class where we discussed the derivation of the Euler's identity and we discussed some corollaries when we derived that identity. So this was one of the corollary of the Euler's identity. So if this is so, then what we can say, that if I multiply this and this number, e raised to power I theta and e raised to power negative I theta, this will give me equal to 1. Why so? Because this will make e raised to power I theta minus I theta, and this will leave e raised to power 0 equal to 1. So this number which is added in this number gives us 1. This number is called the complex conjugate of this number. And similarly, this number is called the complex conjugate of this number. So we can say that if we change the sign of the imaginary part in a given complex number, keeping the sign of real part as it is, then we transform a given complex number into its conjugate. And once we multiply two conjugates, complex number which are conjugates, they gives us 1. the result of multiplication of two complex numbers which are conjugate of each other, the result would be 1. Now see what would happen if we divide two numbers which are complex conjugate of each other. See, e raised to power I theta divided by e raised to power minus I theta, this gives us e raised to power 2I theta. Or we can write it as e raised to power I 2 theta. So what does this mean? Means that the arguments will be added up for if we are multiplying two complex numbers which are conjugate, or if we are dividing two complex numbers which are conjugate of each other. Agreed? So let's move to the division operation. That now, because we just have seen that if we multiply two conjugate numbers, we will be left with the real number only. The imaginary part will be vanished in the product. That's why we are multiplying the denominators conjugate numerator and denominator. We know that once we multiply and divide with the same number, the identity of the reality or the value of a mathematical expression remains unchanged. So similar operation is performed over here. So the upper part or the numerators of these two terms is identical to multiplying two complex number, and we can multiply these two complex number from the operation we just seen before. That will be ax minus ay iota plus bx iota plus by divided by x square plus y square. If you multiply these two things, imagine we are left with only real part, the imaginary part has been vanished over here. So from this we can write ax plus by plus bx minus ay. So again we are left with a complex number with real part equal to this divided by this and imaginary part equal to this divided by this. So say if we are having e raised to power I theta, the representation of this complex number in exponential form, and e raised to power I psi, for example, the representation of this complex number into the complex exponential form, then this gives us e raised to power I theta minus psi. And from this we can write that this is equal to cosine theta minus psi plus iota sine theta minus psi. Instead, let me rewrite this expression for clarity. Using trigonometric identities, we can expand these operations to evaluate the results. Now, the last thing. There are some other mathematical operations that can be performed on the complex numbers, such as logarithms, such as taking square roots. So these operations are tedious. For the moment, we are not going into this very detail, but we are limiting ourselves to these four arithmetic operations which are fundamental in nature, that are occasionally used when we are working with the complex numbers. In some future class, we shall be discussing how we can evaluate the logarithms of the complex number and take the square roots of the complex numbers. Now last thing, as we have discussed that a complex number consists on two real numbers that are written like this. So what would happen if I make y equals 0? Then this will leave us with only x, because This gives us x only. So in this sense, we can say that every real number is a complex number with imaginary part equal to 0. So in other words, we can say that the set of the real number is subset of imaginary number, or is the subset of complex numbers. Let C be the set of complex number. From this we can deduce that the set of real numbers can be treated as a subset of a complex numbers. So in other words, we can say that the universe is dominated with complex numbers. Though for our easiness, we are transforming those complex numbers into the real numbers by making their imaginary part equal to 0. So in this sense, we can say that the main players of this entire mathematics is the complex numbers. So this is a conclusion we can draw from our discussion today. Or in other words, we can say that a real number is a complex number with argument equal to 0. You can say that, say if we transform this number such that y into the exponential form, then its argument will be tan inverse 0 over x. This gives us tan inverse 0, and tan inverse 0 means 0. Why so? Because sin 0 is 0. So 0 divided by anything will be 0. So we can say that a real number is a complex number with argument equal to 0. So that's the end of today's class. In the next class, we shall be solving the examples on complex number using both analytical approach and the graphical approach. For the next class, Allah Hafiz.